Hello, everybody. Good morning and good afternoon. I hope everyone is doing well this fine Tuesday. My name is Alan Pendon, and I am the Digital Demand Generation Manager here at Electron, and I'm excited to present this webinar with Anritsu on PCIe 6.0 Receiver Test Solution. Now, the session will be recorded, and the links to the recording, as well as the presentation, will be sent to everyone after the event. Today's speaker is Hiroshi Goto. Currently, Mr. Goto is the high-speed and optical product and business development manager at Anritsu, where he has worked for over 25 years in multiple roles, including design engineer and product marketing engineer. He has authored numerous industry application notes and white papers, and frequently speaks on the topic of signal integrity. Mr. Goto graduated from Oyama Gakuin University with a bachelor's degree in physics and resides in the Dallas area. Now, before we begin the webinar, I just want to go over a little bit about Electrant. We are the largest testing and technology services provider. We have over $1.2 billion in inventory that equates to having more selections for your testing needs. Electron has invested more than $100 million on new inventory. We have over 122,000 solutions in stock, 27 offices, and inventory centers that can deliver to over 100 countries and over 600 specialists to help you. And right before we start the webinar, if you have any questions, please just put them in the questions or chats panel, and I will address them with Mr. Goto. And with that, let's get started with the webinar. Let me change the presenter here. Yes. All right. You got it, Hiroshi.
Okay, thank you very much. Thank you very much for attending today's webinar. My name is Mr. Goto, and I'm going to present Anritsu PCIe 6.0 receiver test solution. The agenda is, first, I'm going to talk about PCIe 6.0 overview, then talk about what's new for PCIe 6, mainly PAM4 and FRIT for the error correction. Then receiver link equalization test, compliance test, the details, stress die calibration, link equalization training, receiver compliance test, and then this is kind of additional, the jitter tolerance test. Then I'm going to present Anritsu PCIe 6 test solutions. The last three, question and answer. The key benefit of PCIe 6.0, the first of all, double the bandwidth. Almost every 3 years, PCI-SIG increased the speed, and now Gen 6 is 64 gigabit per second per lane. PCIe supports up to 16 lanes. That makes the total aggregation speed will be more than 1 terabit per second. That is 256 gigabyte per second. And the low latency is the key. Using the FRIT, that is flow control unit with fixed size, that allow the very low latency, and using forward error correction, that is a very light forward error correction, and using PAM4 signal with strong CRC, cyclic redundancy check. So very low latency. Then backward compatibilities. Gen 6 device modules must support the Gen 1 to Gen 5 also. So the backward compatibility is the key for PCIe. And a lot of discussion in the like PCI-SIG meetings and also developers conference, what will be the form factor to support PCIe over optical. because backward compatibility is very important for PCIe. So what's new?
Hiroshi?
Yeah.
I do have a quick question. Do you know when the PCIe G6 will start?
So the first for your information test will be held in June, July 2024, so within 3 months. So that is a kind of a for your information. And for your information test will be maybe end of this year. So actually the spec will be fixed early next year. So again, Gen 5 is already now started and maybe less 3 years. So 2026, the actual amendment and utilization.
Thank you.
Sure. Okay, so what's new and key for PCI Gen 6? So PAM4 is a new modulation schemes. Up to Gen 5, PCIe always use NRZ, no return zero. But now PAM4, so 1 time slot, 2 bit in 1 time slot. So 0, 1, 2, 3, 4 levels. And compared to the NRZ, you automatically lose 9 dB SNR. So it's going to be very difficult to get a very good SNR. Then from this picture, you can see NRZ, the cross point is here. So you have a lot of phase marching. But PAM4, because of the TRTF, the edge speed of the signal, the TRTF eats the phase margin of top eye and bottom eye. So you have a smaller phase margin. So to compensate this 9 dB signal to the noise ratio, the forward error correction will be used. And the PCIe 6 use strong CRC, which plays a key role to establish the low latency. So the two key elements, PAM4 modulation scheme and right forward error correction, that is a flit. So new criteria of BER and flit errors. Up to Gen 5, the BER is used of E-12. So almost no errors is expected. But because of the PAM4, now that is not the case. Now, first bit error rate is used to make a criteria of pass and fail. And successive burst errors, like contiguous errors, propagating by the DFE will be counted as a single error. So when the clock pattern is coming to DFE, that may cause a contiguous error, like 101010 can be 010101. It's completely opposite. Then that can be a burst error. But that kind of a successive burst error can be counted one error. And the new criteria is the FBER at the physical layer is E-6, assuming the forward error correction corrects the random errors. And then a successive burst error created by DFE can be avoided by using pre-coding. So pre-coding support correct or avoid the contiguous error created by DFE, and then random error can be corrected by FEC. The concept of FBER is actually when the flit error, so flit cannot correct errors when some conditions, then the condition of flit error rate, if the flit error rate is less than E-5 times 3, so 3E-5, the CRC can be corrected all errors. That is a concept, but it's going to be a little bit difficult to measure frit errors. Then, instead of using the frit error rate, the fast BER can be measured. And when the FBER is less than E-6 or better than E-6, which guarantees the frit error will be better than 3 minus E-5. That means all error can be corrected. Just for your information, the receiver threshold of Gen 5 was E-12. So E-12, almost no errors. But PCI Gen 6, it's always some errors, but can be corrected by CRC and for the error correction. So let's talk about receiver link training compliance test. This is a procedure of RX LEQ test. The most important thing is the calibration, channel characterization by vector network analyzer, and then amplitude preset SJ and RJ calibration by using BAT and real-time oscilloscope. That is a TP3 calibration. Then stressed eye calibration. That is a TP2 calibration. So DMI, CMI, eye height, eye width calibration. It is very time consuming, and the target eye of Gen 6 is only 6 millivolt eye height and only 0.1 UI eye width. That is only 3 picosecond. So it's a very small eye. And to achieve this, the calibration is required, but that is very time consuming. It's like it takes, maybe 2 hours. And then once calibration is done, now link training test. The DUT needs to be looped back under the stress eye conditions. Then once it gets looped back, now you can make a bar measurement. The PCI Gen 5, E-12, PCI Gen 6, fast BER E-6 or better. Then additionally, you can make a jitter tolerance measurement. This is the table of the stressed eye of each generation. So Gen 1 to Gen 6. So Gen 6, eye amplitude is 800 millivolt, and 1 UI is only 31 picosecond, but it is same as PCI Gen 5 because using PAM4, so without increasing the baud rate, you can double the bit rate by using PAM4. The eye width is only 0.1 UI, 3 picosecond, and stressed eye height is only 6 millivolt peak to peak. And differential mode is 15 millivolt peak to peak. So this is the loss topology of PCIe chem specifications. So from root complex chip through the board, go to the riser or chem connector, then add-in card chip. The total loss of PCI Gen 6 is 36 dB, and PCI Gen 6 will be 32 dB from chip to chip. And using vector network analyzer, you need to characterize the total loss to be 32 dB for PCI Gen 6. This table shows the actual calibration of BAT for PCI Gen 6. First, TP3 calibration and measure SJ and RJ. This is a nominal number. Then TP2 calibration for DMI and CMI through 32 dB or 33 dB channel loss. Then once you calibrate TP3 and TP2, now final eye calibration. SJ and DMI is a knob. Basically, SJ is a knob for phase margin, and DMI is the knob for eye height. In this case, the channel pair of ISI 13 pairs, the channel 13 was used, and actual loss of the total is 32.6 dB at 16 gigahertz. And a preset Q5 was used. Optimized EQ for the scope is 14 dB. And we get a final eye height almost 6 millivolt peak to peak, and eye width 3.4 picosecond. So this is in the target. Currently, for Gen 6, new compliance baseboard CBB and compliance roadboard baseboard are ready for the next 4-year implementation test. But ISI board seems like we are going to use PCI Gen 5 because loss can be the same and return loss is similar. So, but you can get information from PCI-SIG. Intel is making this board for CHEM fixtures. This is the actual measurement of 33 dB loss through the pair 32 and fixture, pair 0, and MMPX cables. Now, the RJ calibration. So this is actual data of Anritsu BAT. As you can see, up to 200 femtosecond RMS setting, the RJ doesn't increase, mainly because this is kind of varied by the intrinsic jitter of the scope and also the PPG, pulse pattern generators, but PPGs itself. So the target is 250 femtosecond RMS. This is the target, red line. And actually, the intrinsic of the BAT is like a 180 femtosecond. So you do not have much margin. So when you make an accurate measurement, you cannot make a linear fitting using less than 200 femtosecond because that is kind of an intrinsic jitter, so it's not linear. So you must use the data more than 200 femtosecond RMS, then take a data and find out what is the setting to get 250 femtosecond. So blue, actually not blue, it's a purple line is a real-time scope calibration, and the orange line is a sampling scope, a real-time scope. So you may need to use a noise reduction technique or noise removal technique because some scope has quite huge number of the intrinsic, so you need to remove the noise of the scope itself. Then this is the actual calibration of RJ. Now, from these 3 data points and linear fitting, get the number of the setting. But RJs are sometimes a little bit kind of confusing because the peak-to-peak UI is 0.112 UI, but that is a 3.5 picosecond peak-to-peak. But the spec use RMS number, so you need to change it to the RMS number by specifying the BER. So in this case, E-12, 14 times, but E-6, like 8 times. So different calculation. And in this case, the setting will be 128 UI setting. You get 250 femtosecond RMS. For RX-LEQ test, first and most critical step for stable and repeatable receiver test is establish the return path. So once the RX-LEQ calibration is done, you can start RX-LEQ test. The object of RX test is successful link training under the stressed eye. So your DUT needs to find the best preset and CTLE. So that is optimized equalization. And then needs to go to the loopback. Then FBR E-6 or E-12 for Gen 5. But this BER or bar should come from your receiver DUT. But when you make a loopback, now your DUT TX loop back the same pattern to the error detector. Gen 5, it is quite easy to get error-free, but Gen 6, because of the loss of this return path or back channel, it's going to be very difficult to get error-free. Even, E-6, you need to make optimization from your DUT TX to the error detector. Then this is the procedure. First, you need to minimize the loss and ISI of the return path from DUT TX to error detector. Short and high bandwidth cable must be used. Then, before making the RX test, you just generate the MCP or compliance pattern or any PRBS pattern, PRBSQ pattern from the DUT TX. That is the same concept of TX initial test. So you can do that. You have the capability to do that. Then optimize the equalization. So Anritsu has the eye opener card with CDR. So you need to find out what is the best CTLE, and you have to find out what is the gain to get the best BER. If you cannot make the DUT TX generate a pattern, the best way is make a loopback without any stress. So remove all SJ, RJ, DMCM, and make a loopback. Then optimize the return path. So once you optimize the return path, you may not get error-free. In that case, for example, if you get E-9 from your DUT TX to receiver, then the target is E-6. So the error will be 0.1%. It's kind of negligible. Even if you measure E-6, it's negligible. And if you measure RX test E-7, still 1% error. If you only achieve E-7 from the DUT TX to error detector, still you can make a compliance test because the pass-fail criteria is E-6 FBR. So in that case, error will be 10%. This is kind of a measurement example of jitter tolerance of 100 megahertz SJ. So this is the Gen 6 chip of clock data recovery. So DUT is CDR of Gen 6. Under the stressed eye conditions, the CDR shows between E-10th to 11th. But all error can be corrected. So no bit errors at 0 UI injection of 100 megahertz. Then increase the SJ of 100 megahertz by 20 milli step. Up to 80 milli SJ, no frit errors. So all error in the frit can be corrected by the forward error correction. But at 0.1 UI, that is 100 milli UI SJ of 100 megahertz. Now, frit error, some errors of frit cannot be corrected. In that case, CRC is still working up to 3E-5. So still all error can be corrected by CRC. Then this is E-6, the criteria of fast BER. So when the fast BER is less than E minus 6, seems like all frit error is less than 3E minus 5. So that kind of guarantees you just need to measure FBR, and automatically the frit error will be less than 3E minus 5. Then when the frit error is more than 3E minus 5, which means now FBR is also worse than E minus 6. So this is nice data to guarantee you can use FBR to make the pass-fail criteria. So let me introduce Anritsu Gen 6 RX LEQ test solution. So Anritsu BAT MP1900 is kind of all in one for PCIe Gen 1 to Gen 6. So no external redriver is required. And link training test and LTSSS event is supported. So this is BAT, but protocol-aware BAT, and built-in CMI and DMI and jitter injections, SJ, RJ, BUJ, and SSC, residual SSC also. And the BAT support 3 clock architectures: the common clock, separate reference clock with SSC, and SRNS, no SSCs. Also, the BAT has a function to analyze frit-fec burst errors. So that is a really nice feature. And for up to Gen 5, because of the very good sensitivity, you have a lot of margin on your receiver test. And as I said, the calibration of TP2, TP3 and stressed eye calibration is very time consuming. And it has a partnership with Tektronix and Recloy. And both company, Tech and Recloy, provide the automated calibration software when you use Anritsu 1900 together with their scope. So the calibration can be automated and repeatable and reproducible. When use Keysight scope, GRL provide the automation software to control Anritsu BAT and Keysight. So all 3 major vendors of real-time scope can be mated with Anritsu 1900 BATs. Then, as I said, Anritsu 1900 BAT is a protocol-aware BATs. So not only measuring the PER or FBR, you can analyze the protocol and link training. This is the example of the link training looped back. So when the training starts, you can see every single event between the handshake between the BAT and your receivers. And you can see Gen 1 to Gen 5 translation. This is the measurement example of the jitter tolerance. Up to 20 different SJ, you can automatically measure the jitter tolerance. And then this is the kind of a matrix scan of the PPG's emphasis. So once your DUT pass the LEQ RX test, then you can change the PPG preset and find out what is the best preset from the PPG. You can manually change the cursor or preset and then find out what is the best condition for your DUT. But again, this is also kind of a time consuming. So the BAT has an automated matrix scan of the preset. So you can see this kind of test result: green portion, no errors, and start seeing some errors, the yellows, and red portion is a synchros. And it is very important to start the link training using this green portion. Otherwise, the link training may fail because at the initial handshake may fail if you do not get any information from the parts. For the base spec measurement, this BAT has a very good flexibilities. For example, you can change the pattern, and also you can change the pre-coding, gray coding, on, off. Also, you can give a skew between the MSB and LSB, so it's very flexible. Sometimes, the IEEE use MSB first to encode PAM4, and IEEE is a kind of opposite. PCIe use LSB first, but some chip device use the same criteria, so you may need to change the MSB LSB bit. And these are the pattern we can support by 1900. And also error detector side, you can manipulate the polarity of MSB LSB independently, and gray code on off and pre-code on off. So for the error correction is the new but key. For the physical layer base spec, how do you evaluate the DUT which doesn't have the FEC coding or decoding function? For example, the CDR, it doesn't have coding or decoding function of forward error correction. So some chip has BR measurement capability, but no FEC coding or decoding. So these chips, how do you measure the FEC capabilities? So you have to measure correctable and uncorrectable errors for the error correction. And Anritsu error detector has a function to analyze the errors. And once the error detector detects errors, the error detector can analyze that error can be correctable or not correctable by forward error correction. And pulse pattern generator side, the PPG can generate the burst errors, and that can be or cannot be correctable. So you can clarify, or you can specify, okay, I'm going to insert burst errors, which cannot be corrected by flit. And you can find, what kind of condition the chip may fail, or the error correction doesn't work. So that is a very strong function to analyze flit FEC functions. Then once chip can be looped back, the error detector has a function to measure PAM4 symbol error, first bit error, first BR, and actual raw BR. And you can see in this case, raw PAM4 symbol error and bit is the same. First bit error is almost the same. So that means no burst error is happening. So in this case, flit error, no flit errors. Even FEC symbol error is some E-4, flit error is no error, which means all error can be corrected. And then the error detector also has a function to show the histogram of correctable and uncorrectable errors. For flit errors, 0 or 1 error can be always corrected. 2 or 3 can or cannot be corrected depending on the group of the CRC. So when the same color, it cannot be corrected, but the different color up to 3, it can be corrected. And more than 4 errors, it cannot be corrected. So you can see this kind of histogram. Then this is the details of the errors. So the error detector has a function which transit bit has errors. For example, in this case, level 0 to level 3, sorry, level 0 to level 1 has a major error here. And also, you can measure MSB and LSB. So MSB is the middle eye, and LSB is top or bottom eye. And you can measure MSB and LSB BER independently. And this kind of a histogram in the table. So once you increase the jitter, now you start seeing some errors, but still this is correctable. Then increase the jitter. Now you start seeing uncorrectable errors. So you can make this kind of automated jitter tolerance test using FEC error criteria. Also, the BAT has a function to analyze P and N skew, the positive and negative skew functions. So the left side of the eye is P and N, but N is inverted to see the skew accurately. Then this green trace here is the output of the differential trace of 10-inch. So input to this differential trace, 0 skew, of course, output is 0 skew. When you give 300 milliui skew to the input, now output of the trace will be completely distorted. Now, this is kind of a common mode CM to DM conversion, but you can see input is you can just see the skew, but now amplitude is completely distorted and eyes closed. And when you give 600 milliui, now you can see a very distorted eye. So this kind of skew measurement can be possible using dual channel pulse pattern generator. You can configure single, dual, or quad channel. And once you configure dual channel PPG, you can synchronize the PPG completely. And you can give plus minus 750 milliui in linear, completely linear, no bit jump. So now very good linearity, plus minus 250 milliui, so more than one UI you can see. And if you need to measure like a 2-3 bit, of course you can give up to 64 UI bit skew between two PPGs. Then this is a summary of Anritsu 1900 BAT. So concept is multi-channel PAM4 NRZ BAT from 2.4G up to 128 gigabit per second per channel. And you can configure up to 16 channel 32G or quad channel 116 gigabit per second PAM4. PCIe, USB, Thunderbolt link training, and equalization, and LTSSM analysis. Again, 3 clock architectures, common mode, SR, SS, SRNS. Signal integrity is a great advantage of Anritsu BAT. Very low intrinsic jitter and very fast TRTF. NRZ BAT has 10 tap emphasis, plus minus 20 dB emphasis, and PAM4 BAT has a 4 tap emphasis, also plus minus 20 dB emphasis functions. The error detector has 12 dB CTLE and PAM4 BAT up to 30 dB CTLEs. You can inject jitter 2 tones of SJ, random jitter RJ, BUJ for crosstalk, half period jitter, and residual SSC injections. Vertical noise, CMI, common mode noise, differential mode noise, and white noise, so broadband noise, and also ISI function. the application PCI Gen 1 to Gen 6, Thunderbolt 3, USB 3.1, 3.2, 4.0, and 4 version 2, that is PAM4 and IEEE InfiniBand and optical modules. These are the applications. Then this is the last slide. The Anritsu Gbaud is ready for Gen 7 generation. So it can generate to Gen 7 and you can also inject jitter. Okay, thank you very much. Any questions?
Looking at the questions panel, I'll give it a moment. But maybe you can answer something for me, Hiroshi. You might have covered this earlier. How long will it take to finish the stress die calibration test?
Okay, yeah, that is a very typical question customer ask. Okay, so depending on the application software of each scope vendors, but generally for add-in card 2 hours, host maybe 2.5, so both maybe 4 hours. And you know, the compliance test or workshop, we always start calibration Sunday afternoon to finish the calibration before Monday morning. And Monday morning, we are ready to make a workshop compliance test. So both add-in card and root complex system, maybe 4 hours.
Gotcha. Thank you.
Sure. And then, okay, just one. Okay, so now Anritsu Gbaud has a function to generate Gen 7 128 gigabit per second, no problem. But error detector side, currently 116 gigabit per second is the best to get error free. And Anritsu is looking for a nice eye opener for 128 gigabit per second, 64G board. So if listener has a good recommendation of eye opener or redriver for 128 gigabit, please just send me an email, hiroshi.goto@anritsu.com, my first name dot last name @anritsu.com.
All right. Well, I don't see any more questions, so
Okay.
I think we can wrap it up. Well, everyone, thank you so much for attending.
Thank you very much.
Yeah, no, thank you, Hiroshi, for speaking today, and thank you for Anritsu. Again, as mentioned, the links to the webinar or the recording, as well as the presentation, will be sent to everyone after the event. So again, thank you. Enjoy the rest of your day, and we'll see you at the next webinar.
Thank you very much.
All right. Bye-bye.